I think somebody, when I went in for the first time to this room, it says recording in progress, so it might be that we are recording somewhere. Okay. Sorry, everybody, we are a little late, but we have a good visitor here today, Lalitha Sairam from University of Birmingham. And then you're going to University of Cambridge, right? Okay, you can tell us about yourself a little more.
Yeah.
And then we will start off.
Sure. Hi, everyone. I'm Lalitha Sairam. So I'm currently a postdoc at University of Birmingham, where I do not work on STACCATO, but this is kind of my passion, so I still keep doing it in the side, where I work on circumbinary planets. But later in summer, I'm moving to University of Cambridge, where I will legally work on stellar activity and continue my work on this thing that I will talk to you today. So as I said, currently at Birmingham, what I am focusing on is developing new methods to precisely measure the radial velocities of double-line binary stars. So these are one of the most common binary stars that we can see in our solar neighborhood. And they are intriguing system, but because double-line binaries spectroscopically, they are very challenging. They create wiggles when it comes to standard methods of measuring radial velocities. So people have avoided this most of the time. So I was hired to come up with methods to solve this problem somehow. And I'm glad to inform that we have two new methods, and that has started yielding planets. And here's one of the planet. This is a tattooing-like planet, which will be coming out soon. So look out for this space. However, what I'm happy to see is this method currently performs much better than traditional way of measuring radial velocities, which is shown here in yellow. And hopefully we can increase the population of circumbinary planets that has been seen. And we have better understanding of young planetary system and how planets are formed in general. This is two papers which are in progress. So it should be out in another month or 2 months time. So if you are interested in circumbinary planets, look at it.
So what is the traditional method?
So traditionally, for double-line binaries, we use the cross-correlation method. So this is the two-dimensional cross-correlation. So because there are two stars, you have two templates that is, or two temperature templates that is used to cross-correlate, and you get the CCF and measure the radial velocities from that. But the problem is how precise these templates are does matter a lot when it comes to these binaries, because when you do a cross matching, what you get is when the template and the spectrum matches each other, you get the deep Gaussian-like profile. But when you're matching each other due to coincidental correspondence, in the sides of this Gaussian profile, you get these wiggles.
Okay.
And when it comes to double-line binaries, there are two sets of wiggles and two deep signal. The signal is fine, but then interaction of these secondary wiggle with the primary signal affects the precision, and that introduces 15 to 20 meter per second scatter in the radial velocities. And if there is a Jupiter-Mars planet around these stars, that is completely hidden in this noise that is produced. So that is the traditional way of determining. So the current method we can reach, depending on the star, of course, anywhere between 6 to 8 meter per second for the primary star. And in some cases, we reach the photon noise of the instrument itself. Hopefully we can improve further based on what we have currently. But if you're interested in knowing more about the method itself, we can have a chat at any point of time. But today I thought I'll speak about stars when they misbehave and what kind of impact that has when it comes to exoplanetary science and how we can try and tackle this itself. So I grew up in India, and one astronomical object that was abundantly available was the sun. And not surprisingly, I started my academic career looking at the sun. And for me, sun is a very unique body because of its proximity to us. It allows us, of course, the high resolution observations, and it also allows us to carry out high contrast images of the surface, which is crucial when it comes to other stars where it's not really resolved, and we just draw conclusions based on what we know from the sun. But it's not a one-way traffic. We do learn a lot from stars as well, because stars come in so many flavors. They have different temperatures, masses, rotation period, and so on. So it allows us to place our sun and time as such. And this has been something that that was the primary focus of my early research itself. And one of it was, of course, looking at flares that I concentrated on to look at solar flares and compare them with stellar flares. So it can be assumed to be analogous in the stellar flares to that of solar flares, where we assume that it occurs as a result of magnetic reconnection, which is shown here in the schematic diagram. When we see a magnetic reconnection, which occurs at large coronal heights, what we expect is the electrons to start accelerating downwards towards the chromosphere and reaching the chromosphere and evaporating the material, because we are speaking about electrons moving from coronal heights all the way to chromosphere, which is of 10,000 Kelvin or so. And these evaporated material, when they fill up the loop, then we start seeing X-ray flares, especially soft X-ray flares, and so on. So when it comes to flares, we do see across wavelengths in sun, and of course, we do see similarly in other stars as well. What you see here is a recent observation of Proxima Centauri, our nearest planet hosting star. And this was part of a multi-wavelength campaign that we carried out a few years ago. On top, what you see is ASTROSAT's soft X-ray telescope. So ASTROSAT is a multi-wavelength space-based mission that was launched from India in 2015. What you see on top is just a soft X-ray observation of this. At that point, key interest was to actually look at how well ASTROSAT performs without any intention of doing any more science beyond that. But then Proxen being Proxen, it flared. So we had ASTROSAT and Chandra observation at the same point of time. And we also had some Hubble observations that was coordinated. So the two vertical lines that you see here indicate the peak of each of the flare. The first one is the UV peak, and this is the X-ray flare peak that was observed, suggesting that if you see the UV peak peaks earlier than the X-ray flare, and this is indicating that the electron impingement takes place earlier than that of electrons filling or the evaporated material filling up and producing X-ray emission. This is very well known in our sun and called as Newport effect, and it's nice to see that in other stars, which raises a lot of questions because this is Proxen, which is around M4.5 spectral type, raising question about what kind of flaring mechanism is producing this, because our sun is an G-type star. So what kind of dynamos are in action and so on. So this is what I used to be interested in the past. However, what was even more interesting is to see how these flares play a major role when it comes to planets that are there around these stars as well. Because stars like Proxen can produce several flares per day. And if there is a planet, which we know Proxen has, then continued exposure to such environment can in fact affect the habitability of planet around these stars. When we speak about radiation from the host star, especially in optical and infrared radiation, these play a key role when it comes to the surface and the lower atmosphere of a planet. Whereas UV and X-ray play an important role when it comes to the upper atmosphere of a planet, because the UV radiation usually gets ionized in the atmosphere, whereas X-rays penetrate a bit deeper. And the free electrons acquire momentum. And as the X-rays are absorbed, these momentum, the electrons with excess momentum tend to scatter each other, and that is increase in temperature in the atmosphere. And as a result, what we end up seeing is the atmosphere being irradiated or being lost eventually. So if we assume that a planetary atmosphere is made up of hydrogen or helium, and all the X-ray and UV emission from the host star is absorbed by this atmosphere. This is having lots of assumptions in this case. But if we do that, then one can in fact estimate the amount of mass that is lost by the planet, which is directly dependent on how much X-ray and UV flux a planet receives at its location. But looking at our sun and looking at other stars in our neighborhood, what we do know is a star is not constant. It is much more active when it is young, and later on it kind of plateaus in its activity. So if you take that into picture and the amount of mass that a planet has lost, you can kind of get a picture of mass loss history of planets. And these are 4 different planetary systems that I felt looked interesting at that point of time, but now there are a lot more even interesting planets. But these 4 shows 4 different systems at different ages. And what you see is the mass loss plotted as a function of its age. The circles over here indicate the current age of the system, and taking the age of the system and the amount of mass that would have been lost, integrating backwards. What you see is this nice curve, which gives us an indication of the mass loss history. If we assume, for instance, 55 K3e, the current mass of this planet is about 8 Earth masses. And if you look at this plot, it suggests that as of today, 55 K3e could have lost anywhere between 10 to 12 Earth masses or so, stating that when the planet was formed, it may have formed as an 18 or 20 Earth mass planet. It has lost 10 to 12 Earth masses, further indicating that if not all, most of the primordial atmosphere of this planet is already gone. If one detects oxygen or O3 from the planetary atmosphere of 55 K3e, one has to be extremely cautious, because this oxygen or O3 need not be produced due to biological activity, but purely due to photodissociation because of the irradiation that we saw from these planets. So that is where such study, knowing the history, knowing the X-ray flux of the system, plays a crucial role for all these planetary systems. However, this is important when we do discover an Earth-like planet in its habitable zone. If we ever detect the atmosphere where there is oxygen and O3 around these planets, because these are all most of them planets which are around M-type stars, except for Kourou 7. But today, the challenge. Yeah.
Sorry, that mass loss equation, is that just thermal mass loss, or what goes into that briefly?
It's just purely based on the amount of flux, that's it. There is no other thermal component into it. The post
What's driving the atmospheric loss, though? Is it pure thermal escape, or is it ionization being carried by wind?
It's irradiation due to thermal. The irradiation due to the planet itself swelling up and losing its mass. It may not be due to atmosphere, wind driven, because then we have to assume or make complicated math. We didn't want to get into complicated math.
And what is that, like, I'm understanding this calculation December assume that the planet was always in the center.
Yeah. There is no migration, nothing. The planet was born at that place. In fact, it does not apply for our solar system planets.
So when you turn the argument for that, this is the maximum mass that the planet is 2.5.
Yes.
Okay.
Yes, exactly.
That's very nice.
Yeah.
Yeah. So do you have to assume that this, what was it? It lost 11 Earth masses and it's left with 8. You have to, am I remembering more or less right? Do you have to assume that this 11 was atmosphere, nothing rocky or solid or?
So, there's quite a bit of assumption, as I said. These are assuming that these are Jupiter mass. When they formed, or no Jupiter mass, Jupiter-like planet, or this entire work originated from the fact that we wanted to know whether evaporation of a planet from Jupiter mass can allow us to understand how smaller rocky planets are formed nearer to the to a star. So that is the origin of it. This relationship more or less works best for Jupiter mass planet, where you have the Roche lobe also taken into consideration, and you have the right balance over there. However, this is the most simplest basic assumption. It is not true for all cases, and it does not explain, for instance, how TRAPPIST-1 system has all these planets, which is at this location. However, it can kind of suggest what could have been the fate of this planet. If that is water, will the water remain in the planetary surface at all, and things like that. So currently the main challenge itself is in detecting these Earth-like planets. When it comes to discovery of smaller and smaller planets, we are relying on the radial velocity technique to measure them spectroscopically, where we try and measure the reflex motion of the planet. Sometimes the same amount of motion can be produced due to spots on the surface of these stars as well. So that is where the challenge remains. So what you see here in this plot is a simulation of two Earth mass planet orbiting around an M-type star. And shown in black is the planetary data, along with some jitter that I've introduced due to stellar activity. So this is how usually the data looks. However, if there was no stellar activity, it was a simpler case, then what you would have seen is just the red curve, the variation in the radial velocity data. But the moment stellar activity comes in, the planetary signal is completely lost. And that is one of the biggest challenges when it comes to the finding planets using radial velocity technique. And the second one is sometimes stellar activity can in fact mimic the presence of a planet. So this is the case of an actual observation where it was first claimed to be a planet, but later on debunked due to the rotation of the star itself, it was associated with the stellar activity. So this is the biggest issue when it comes to finding smaller and smaller mass planets. So when it comes to stellar activity, we have various time scales that we look at. So most of them assume that magnetic activity cycle does not matter. The stars have long-term trend, and however, what is more challenging is the shorter-term trend when it comes to observations. So magnetic activity cycles, usually we speak in the scale of months to years time scale. But what people have been bugged about is at shorter time scale of days, which is the rotation of the spots or the rotation of the star itself, which is modulated in the form of spots or plages on the surface of these stars. So this is measured to some extent, and we try and solve this, but this is a big issue. I'll just get back to it in a little while. But there is another issue that we see in the data, and that is additional noise that we see in radial velocity data, which is due to granulation on the surface of the star itself. So, what we see is there's a lot of scatter in the radial velocity data if you take a time series of radial velocity data, and this is usually due to granulation. So what we often do as an exoplanet observer is to take 3 or 4 observations per night for each star and separate them over a period of 2 or 3 hours, so that if there is any variation, we just try and reduce it. If there is nightly scatter, we try and remove it, which could be due to granulation, which is of the order of days time scale. And other thing that is a big issue is the low amplitude variation in the data, which is oscillation. On Sun, we have the P mode oscillations, so which has a time scale of 15 minutes or so. To tackle this oscillations, what we do is expose or take your observations for even if you reach a signal to noise ratio within 10 minutes, you expose your spectra to 15 or 16 minutes to just drown out any oscillation that is there in the oscillation signal that could be there in the data. So these are very well accepted and a commonly followed way of tackling stellar activity by most of the people when it comes to observations. However, an additional thing that people do is carefully select the sample that we are looking for planetary candidates around them. So one such survey is Commonness. So Commonness was an instrument that was built for the 3.5 meter telescope at Palo Alto. The main aim of Commonness was to carry out a dedicated radial velocity survey to detect Earth-like planets in its habitable zone around M-type stars. For now, people have been avoiding sun-like stars because of all the activity-related issues and look at M-type stars where habitable zone is much closer to these stars. So Commonness was observed for 5 years. The survey carried out for 5 years. And with 5 years as a fixed term that was there, we had to choose the survey targets carefully. So we decided to go for stars which were not active and look at about 300 stars around that time. So I joined the Commonness Consortium as a first-year PhD student, and I was given the mammoth of task to choose those 300 stars, and I was told that if something goes wrong, you are responsible. A great way to welcome a PhD student. But what I did was characterize these M-type stars within our solar neighborhood. I looked at about 3,000 M stars, and the best way to do that was, of course, at that point to look at Rosette survey. So based on Rosette, I obtained this histogram. This is the LX elbow activity indicator. Shown in red are those stars which were detected, and shown in beige are those which were not detected. That was the upper limit estimate. So arbitrarily, just wanted to reduce the sample size. I divided at LX elbow of around -4, and removed all these stars on the right-hand side, and looked at only the stars on the left-hand side, which was nearly 60% of the sample. However, if you can see, most of these stars on the left-hand side were not detected. So the second problem came in that these in turn could have been more active stars. What we did was to carry out ground-based chromospheric observations to get LH alpha elbow. And then we further reduced the sample to 345 stars, and for which Calmness survey was carried out. And as of today, there have been about 60+ planets that have been discovered by Calmness, and many more in the pipeline. Although these stars were carefully selected, it does not mean that there's no activity, because the stars still rotate. We still have spots on the surface of these stars. So that's where survey like Calmness, what we do is have a ground-based follow-up campaign. So what we have is we know that spots or plages on the surface of these stars are quasi-periodic in nature, because we have the rotation of the star, which is more or less periodic, and we have the active regions on the star, which is constantly evolving, and new regions are born and evolving. So the first term in the equation on top takes care of the constant evolving and decay of the active region. The second part of the equation takes care of the periodic nature of the star. So by constraining these using Gaussian processes, one can in fact model any variation with those stellar activity and detect planets which are lower in mass. And the lowest mass that we could reach was about 1 meter per second in semi-amplitude for these planets. Despite all these methods, despite follow-up, despite knowing how to observe and what not to do, stellar activity can still penetrate through other issues. So what you see here is all the exoplanets that have been discovered since 1992. And plotted along Y is the mass of the planet, and X is the discovery year. If you look at orange, these are the planets that were discovered by radial velocity method, where we get the mass. There has been a logarithmic increase in the number of planets that we have discovered, which are smaller and smaller mass. You can see linearly with time. But as of a decade ago, we just reached a plateau. And this is despite the fact that we have better instruments today. We have techniques like Gaussian processes, which can model stellar activity and so on. And despite that, we do not see planets at masses which can translate into semi-amplitude below meter per second. And the culprit here, of course, is stellar activity to a large extent. So, as I said, stellar activity does drown out a planetary signal if it is there, or in some cases, it mimics presence of planet. But what we see is stellar activity is also creeping in when it comes to atmosphere of the planets, when we are trying to detect them sitting here. So what you see on the plot on the right-hand side is TRAPPIST-1 system. And a few years back, there was a discovery of water feature in TRAPPIST-1b that was published. However, later on, it was debunked to be a feature that was due to spot on the surface of the star, and it was not modeled correctly. And in fact, we see that stellar activity leads to contamination in the spectra, transmission spectra of planets. So, although we have modeling techniques, it still currently seems to produce false detection of both planet and the atmosphere. And it is costing a lot of money when it comes to observers, and a lot of people have got their proposals rejected because it has been oversubscribed telescopes. But what we do is observe a star during stellar activity and ignore that data because of.
So can you explain what's on this graph on the right side?
On the right side,
Yeah.
so this is the transit depth in narrow band photometric observation.
So you're looking at the star and the planet crossing the star.
This is the transmission spectra. So you take the spectra when the star is in front, and then when it is when the planet is in front and when the planet is behind. You remove the stellar spectra when the planet is behind. Then what you're left out is with just a planetary data. So, but this is a transit observation with Hubble, if I'm not wrong. It was a narrowband photometric observation in those region where transits were taken at different during in transit and out of transit. But this was not the debunked one. The one before this was the debunked one. Yeah. So despite all the effort that we have done so far, stellar activity seems to continue to affect, and we thought it's time to think outside box, and that is where I would like to introduce you to STACCATO, that is stellar activity forecast for optimal observations. I wish there was a drum roll for this when the slide comes, but to explain what STACCATO is, I will go back to where I started. I'll rely on our sun. So Hubble telescope has been observing our sun as a star, and it has been obtaining disk-integrated radial velocity measurements of our sun over the last 6 or 7 years. And one of the key characteristics of our sun itself is its 11-year activity cycle. So if you look at Hubble data, initially it observed a bit of the previous solar maxima, and a large bit of it was observed during solar minima. So if you divide this data into solar maxima and minima and look at the radial velocity data, the RMS scatter of this data alone, what we see is it is sub-meter per second during activity minima. And whereas during maxima, we know that there will be more spots, more jitter. So there is more RMS scatter, which sounds very obvious to most of us. But then it does play a key role when it comes to observations of a star. So if we take this radial velocity data during minima and maxima and fit this data with Keplerian parameters, so you use some semi-amplitudes, some eccentricity and periods, create a grid, what you get is a complex plot like this. So what you see here is posterior distribution of semi-amplitude and period. So I take a range of periods and a range of semi-amplitude and use nested sampling and obtain this posterior distribution. And I do this on activity minima data separately and activity maxima data separately. And that is what you see in red, that is during maxima, and in blue is during minimum. And if you see this clustering here, the region that is actually due to our solar rotation, which you can see as density in the data even during minimum. However, one of the key points to note here is if you look at a sun as a star sitting outside, and if you are looking for, say, a period of around 100 days, if there is a planet with a period of 100 days, and if you observe a sun during activity maximum, then the likelihood of detecting a planet stops at Jupiter mass. Whereas the same star, you look at it during activity minima, your sensitivity improves by 2 orders of magnitude, where you can reach Neptune or sub-Neptune level of detection. So in this case, all the planetary signal has been removed from the data, and then we do this test to see what is the impact of observing a star during maxima and minima. And that is what STACCATO is. So STACCATO is looking at stars during its activity minima. So for that, what we have to do is to know stellar activity cycles and to forecast the minimal time, then it would be the most optimal for observations. And STACCATO aims at creating a grid of times where it is at this phase, that is the blue phase for other stars, to carry out observations. So this is again the case for sun that I showed, but what it would look like for other stars is not so beautiful. So what you see here is one of the stars which shows some kind of variability during activity cycle. And the green regions indicate the most optimal time for observing the star based on what we saw for the sun. And this is based on simple sinusoidal model for predicting activity cycles for the star. And STACCATO is built for all these stars that were part of some kind of exoplanetary survey in the past or some kind of survey in the past. So we are currently using all the archival data to build this repository so that anyone who wants to observe at any point of time will have an information about whether it's the right time to observe your star or not. And it need not be during minima alone. It can be during maxima for whatever size case that people are interested in. And as I said, STACCATO is not essential only for detecting a planet, because this example here shows for detecting a planet, but it will play a huge role when it comes to atmosphere as well. So what you see here is 4 of these stars systems that were observed by JWST early release science phase. So there were about 135 hours dedicated for ERS phase on JWST, and 65% of the time was dedicated for transiting community to do the atmospheric work for these 4 systems. And what is interesting is if you look at the blue and the cyan curve, that is WASP 79 and WASP 39 system. Those two were heading towards activity minima or were in activity minima when the observation was scheduled for JWST data. And what was interesting was this was the one of the first papers that came out from JWST observations of atmospheres for WASP 39. And these are transit in various bands that were observed. And the transits seem to be squeaky clean, suggesting that the system, the star looks like was not really active, which is consistent with what we predicted, but then it could have been just purely by chance. So because we do know that stellar activity can be completely random. It need not have any well-behaved
What spectral type are those stars?
these are K. Most of these are K-type stars, at least. They were not cheated. And this is the extension of the same plot that I showed previously. And this is the same as the sinusoidal curve that I showed. But what you see in red are those cases when the star is in its activity maxima. Danger, do not observe your star if you're looking for planets or for atmosphere. The bluer the region indicates the most optimal time for observation. And these are 21 objects that will be observed by JWST or is being observed by JWST as a part of guaranteed time observations. And as you can see, significant number of them are currently in their activity maxima phase. Nothing can be done about it because scheduling these are already painful, I understand. But if people are part of the observations, it's just to give them a disclaimer that maybe try and have a quasi-simultaneous observation from ground to do your photometric observations so that one can model the spot-related variation that you get in data, and you do not claim the feature to be atmospheric if it isn't. So it's like a warning trigger for people like our weather warning system. And the idea behind this entire staccato came because I had 3 or 4 continuous rejection of proposals because of oversubscribed telescopes. How do we free up the telescope time? And by scheduling the observation at the right time, we can in fact increase the efficiency at which we observe exoplanetary targets, because most of the current telescopes have dedicated time, as I showed for ERS or GTO observations, which will give a chance for more proposals being accepted, increasing the efficiency of exoplanets and other researchers as well. And one of the byproducts of this work is because I'm looking at so many stars, building these models, we have activity cycles that are being built for nearly 5,000 plus systems, which will hopefully enable us to build a stronger solar stellar connection. In Birmingham, we have a strong astroseismology group to also look at seismic variability and its relationship with activity cycle. And we have recently launched a program to look at active stars, because most of the radial velocity survey so far has been around inactive stars, because it's the best way to avoid activity. That's what we have been doing. But active stars, we know that are usually young. So if we do detect planets around them, then we are probing into planet formation, and also maybe able to look at ongoing irradiation of the planet, connecting it back to the earlier part of my work. What is next for Staccato is we are building an enhanced forecasting model. Most of the model that I showed is based on a simple sinusoidal model. And if we know one thing from looking at sun for decades, is simple is not good enough. Here you can see a solar cycle. This is from Mount Wilson calcium HNK observations. And you can see each of the cycle is so different to the previous one. So we are currently building hierarchical Bayesian model to be able to learn from the one for each of the star to learn from the previous cycle, the amplitude of the previous cycle and so on. And also to increase the sample size so that we can build a Bayesian model to be able to predict activity cycles more precisely. So yeah.
So I have a question. So this is based on the measuring the spots on the sun, or how do you? I don't
this is
know.
calcium H and K. This is the chromospheric emission lines.
Oh, okay.
So it's due to the active regions on the surface of sun. So Mount Wilson has been going since 65, I think. So that's one of the longest data set that I could come across for sun, which is not focused on a single spot or a single region, but then more as a disintegrated observation.
Yeah, but I just wondering because, you know, there's the sunspots numbers going back to
Yeah.
200 years, right? So,
That's the
No,
S index.
so that's S index, but
Yeah.
the sun is not going down. Oh, no, how?
No.
many years? There's no doubt.
This is just from 1965
Yeah.
S index. I understand sunspot has been going down. So this is part of a project one of my students in Birmingham is doing. There's someone else who's doing on sunspot number. And
Yes.
I am more a spectroscopist, so I've been sticking to this. My issue with sunspot number is how reliable, because it's based on counting and it's from various sources as well. So to look at the trend as such, I thought it would be better if I stick to calcium HNK1. And second is sun will just give one model that is really good.
Yeah.
But for stars, I will look at calcium H and K. So I just wanted something that will be closest to a star and can learn from this and then apply to other stars that might be simpler.
This was actually one of the questions I had in the field of doing the organized scale in that meeting. So could you use something like transfer paper like the train the organized scale, not for the sun of the stars, and then use that as a is that possible?
So currently, what we have not used tests because the time scale is not good enough, right? Because we are speaking about years time scale in this case. Kepler, yeah, but then it's just again constraining to 4 years or so. So what we have done is use ACES and try to constrain that, but then photometric data has been a bit troublesome somehow with respect to cycle at least. Spectroscopically, especially calcium HNK, seems to work much better when it comes. However, a part of the work is using photometric data and to look at also those stars where we have both calcium HNK and photometry to constrain these time scale, get a relationship. So these are all part of the 5,000 stars that we are looking at, how many ever have these relationships. And it's also part of the hierarchical model that we want to build to use all these. But then we are speaking about a smaller sample of around 100 stars or so, for which we have both calcium HNK and photometry to be able to constrain it well and to use that for all other stars. And this works well only for FG and K. So this is no end stars, completely avoiding because they go bonkers. So we just trying to avoid them completely. But that's something that hopefully in next 1 or 2 years we'll have a better insight into.
For astroseismology, now does that give you a problem with, say, K-stars? You mentioned that being one of the challenges.
Yeah. Do not know. So based on how many, it's one of the things that we want to look at, but I've not looked at it at all. So I started working on this as a side project, and over the last 1 year, I've just looked at about 800 stars or so and building the model. So I've not done anything beyond that. So hopefully in a year or two's time, we will have an idea about astrophysics. Do you mean about the oscillations and P modes?
Yeah, yeah.
Okay. Yes, it is a problem, but not at this level. We hope to find a correlation that could be related to activity cycle, and if we can apply that, but that's not a work that we are looking at right now. So one of the main things that I wanted as part of this project was to have this as open source, so that people don't repeat this, and it's painstaking task to go through archive and know whether your star is optimal for observations or no. So this entire database will be available for the community to use it as open source, to type in whatever star that they are of interest for them, and to be able to know what phase the star is, so that going forward, if people are scheduling their observations as a part of, for instance, ESO, if you are looking at whether the star is above horizon or not, whether the weather is good or not. Similarly, to have an additional factor where your star is active or not, whether it covers your science case or not. So that is something I'm trying to pitch to people to have it as part of their observations. Currently, STACCATO is already available for some of the live projects and upcoming projects. So if there is anyone who's interested in knowing about their star, whether it's during activity minima or maxima, please spread a word. I should be able to give them the forecast for any star that may be of interest until the open source catalog is available. The last bit that I want to speak about is just ACtNet. So any forecast needs updating. So you get some new data and update your existing inherent model that is there in your data to improve your prediction. So to do this, I am currently organizing multi-site network of telescopes. These are not new telescopes. These are existing, old, underutilized telescopes, which are not stable to do radial velocity observations, but stable enough to get calcium HNK measurement or photometric observations. So currently there are about 6 partners, and there are 2 more that I am trying to negotiate how much time per semester and things like that. So currently working towards fast-track commissioning of this network. If you know any telescope, or if you know anyone who might be interested in being part of ACtNet, working towards building a legacy of activity cycles, please spread the word. So with that, I'll conclude my talk. I hope I've convinced you that stellar activity is indeed a nuisance, and depending on level of activity of the star, what I've seen is anywhere between 10 to 50% of the observations are affected by stellar activity. And what we do is remove these data or overcorrect for stellar activity, or we have false detection. Currently, the methods that we have are expensive. They are time consuming, and they still do not reach the accuracy that we need. So the way forward is to go hand in hand with stellar observers, and to schedule your observations of the right star at the right time. So thank you.
You took away my question of the time scale. So, when you do the prediction for what for the years, that assumes a whole right?
What do you mean?
Basically, the sinusoidal thing.
Yeah. Yeah, that is simplest model that we assume. Because in fact, WAS39 and WAS79 does not have enough of data that covers large time span. So the rotation period of these stars are very well known. And there is a strong correlation between rotation period and activity cycle. So using that, I in fact have prior and then use sinusoidal model based on the data where the phase is known and predict what would be the phase of the star. But of course, that will be improved if I can take new observation and then feed it into it and improve the prediction.
Excuse me, can you repeat the question, because some people ask us to repeat the question.
Yeah.
So it was the prediction for the human standards. Like including the
So the question was if the prediction for ERS targets was assuming constant time evolution and not using the enhanced forecast. So I hope you've heard the answer. Do you want me to repeat the answer?
Oh, okay, Jeff has the question. Okay, Jeff, please unmute yourself.
Yes, thanks. A very interesting talk. One issue that I don't think you discussed was the variability that sort of doesn't have too much obvious predictive power because it's kind of white noise. Like the analog of the solar granulation and so on. But in principle, that provides some information that could be useful in planetary detection. Have you thought about that at all?
So I have not bothered about it because to some extent the granulation part we are trying to get over it by scheduling observations 3 or 4 times per night, so that you kind of remove any white noise jitter that might come into the observation. So, however, that currently at least does not affect to the or rather I should put the other way around. The rotational induced variability seems to overpower the granulational induced variability, at least at this phase. So I thought, let me tackle the larger scale first and then worry about smaller scale. So hopefully when we have larger sample, we'll have a better insight. But I do know Nadish Munir, she and her group have been working on towards how to handle variation in granulation time scale, but I'm not aware of the details of their work.
Okay, and also, if I understand right, you're kind of using power spectrum or autocorrelation information in the predictive model, but there's also the phase information. That the power spectrum is just kind of half of the information. The phase spectrum has the other half of the information in some sense. I think by looking at your paper, you have a phase parameter, one parameter in the model, but that's not the same as utilizing the full phase spectrum. So have you thought about that? That is using the full Fourier transform of the data, so to speak, including the complex phase as well as the amplitude that gives you the power spectrum.
Yeah, so that is part of our second part of the work that we are working on. It comes in our enhanced model that we are building, which takes into account the full phase information. So the first one was just purely simple Fourier transformation without much of phase information that we take in. That is true, but we just wanted it to be a proof of concept that it is possible at that point. Worry was not to improve upon. However, right now, or not right now, later this summer, I'll start working on implementing this improved model, which takes in all the information. And hopefully that will give us a bit more precise information about the activity name. But however, one thing that we did notice looking at our sun is the precision for sun is also not that great. So we are not really bothered about very precise forecasts in this case. But for instance, for our sun, the activity cycle prediction has a error of around plus or minus 4.5 to 1 year. And we are fine with precisional error of around that when we have so much data for sun and we can reach only so much. For stars, we are not really going to be too bothered about extremely precise forecasts.
Okay, thanks a lot.
Well, thank you. You got more questions, Nathan?
I have one more thing. So when you were using the Hertzman data, and you showed this figure where you had the detection limits, you can like doing maximum activity and minimum activity. Doesn't mean that we will never detect an error, right? That's because that's very tough.
That's true. This is just the number of data points is very little in this case. I think the sensitivity, the detection limit will go better if we have more and more data. So this is about 400 data points, which is within a small narrow band observations. Although HAPS has been observing for 6 or 7 years, I think the data that was available was for 3 years data span. So within the 3 years, I think this is the sensitivity that we can reach. Hopefully when they have the next data release, we should be able to increase the sensitivity, definitely. Yeah.
And this does not include anything like us and processing.
No, nothing complex. It's just purely Keplerian, but using some nested sampling. Yeah, but I think HAPS not, when they give the data, they remove the planets from the data and give it. So it's after all the planetary signal is removed from the data.
Okay. So it's all in your paper.
Yeah. Yeah.
Thank you. Thank you, everybody online. We are signing off. Thank you for joining us. See you all soon.
Can you repeat that out for a second? I just want to see if I can play with the monitor size. It seems like it's chopping off a little. It's dropping off a little.